came into this industry, as was said in the introductory words there, I started off in as a pharmaceutical engineer. All my degrees are computer and electrical engineer, but I started as a pharmaceutical engineer. Two reasons: there's a huge drug culture and community in Research Triangle Park, North Carolina, where I live, and two, I started there as an engineer, and like ink and water, I spread into the chemistry aspects of it. 7 years in, I decided to step away from that and get back to what my degrees were, because it's really what I wanted to do. But I was shocked on day one as I stepped into my first role as a schematics guy in the world of computer design, because I was handed reference diagrams for how to wire things up. And I thought I just walked away from a pretty good pharmaceutical engineering job to do reference schematics. Like, what have I done? So I immediately started at that point, and I spent the next 18 years looking for the thing that would allow me to do something different. I met some of like these giants and legends of the industry at the time, or like I was involved in the days of the design of the first mouse or the first x86 server, and I'm like, wow, when am I going to get a chance to touch on something like that myself? Well, that came about when I stepped into the flash strategy in the early days. The first flash device I ever touched was, if memory serves me, in a development point of view, the first device was a 1 gigabyte flash device that cost several $1,000s, and you had to fill out paperwork as a chain of command as to who was in possession of it. It was like a piece of gold. Early days, and things have really, that's like a few cents now. So that was the first step. And the second step towards this, doing something that's new and different and having a chance to actually change the industry, I think is right now, this change in what's happening in the data center. And the idea is building a solution out of building blocks that's actually built to exactly what you need without over-provisioning, without having to pay for expensive software, and a surprisingly large amount of open source and open hardware designs being a part of it. It's surprising how well the industry's come together to allow this stuff to happen. So first, we'll talk a little about the history and why it's happening and the perspective behind all this. The core behind growth of computer really started as we stepped into the SAN. So SANs are great. SANs are expensive. SANs allow you to do some things you couldn't do before. Large capacity, sharing, but it was complicated, very expensive, still very expensive. Proprietary hardware and software for the most part. Management forces a lot of vendor lock-in. It's not the world of open hardware that you're seeing today. It's difficult to administer. Some people will stick with a SAN technology that they've been using for the last 10 years simply because they've got people with 10 years, 20 years experience on this space, and it's complicated to switch to someone else's. So in a lot of cases, maybe you need your own separate fiber channel network, things of this nature to make this happen. So there's some issues. And a lot of this, when things happen in the industry, it's usually the result of some pain. And what you see right now with DAS, and to some extent as people moved to NAS type designs, it happened because of the expense of SAN. Matter of fact, you could make the argument that the first large capacity SSDs was an opportunity for people who had, we'll say, moderate capacity needs tied to small compute needs that were forced into a SAN simply because they couldn't get the capacity in the box. And so we start giving them 4 or 8 terabyte SSDs and allow them to pull off of a SAN and save money. So NAS is a similar story. People step into NAS because, well, it's cheaper than SAN, and I can give up some of the SAN type overhead and some of the features. And one of the things about SAN that's great, but it's also problematic, is the way it's designed. Everything has to be bulletproof because it's the be-all, end-all of your data center or of your solution. And when everything's bulletproof, that means every I/O cache is mirrored, every wire is mirrored, every path is mirrored, every RAID controller was mirrored, everything was double, and it was very complex to test, things of that nature. NAS did away with a lot of that and was simpler and covers, everything's a shade of gray. Nothing I say is going to be this solution works for everyone. There's always the exception to the rule, and sometimes multiple exceptions. But NAS is another shade of gray that works in some cases, but in other cases does not. And some of the cases where it did not, and you can't cover it with a SAN or NAS, you'd spill into DAS, and you see people, in the early days of online backup, you'd see people who'd take a compute box, an x86 box. They need almost no compute for the online backup stuff. You have some type of RAID engine, and then you'll cascade a bunch of DAS boxes off of it. Very cheap, run RAID 6 or whatever in the early days. You just run simple RAID instead of erasure code. You'd cascade a bunch of stuff together. And this is great in applications like that, but in other applications, if you're building a mission critical box, in my previous life as a solutions guy, an OEM for server design, one of the things I would see was almost every customer. This is a rule of thumb, but a rough rule of thumb, 60 to 70% over provisioning on anything that was business critical. The idea, even I worked at IBM, System X was the lower end of the brand, but even business critical inside IBM, rough rule of thumb I would use was 60 to 70% over provisioning. The idea was, this box is going to run for 5 years. I don't want to ever really take it down. I need the processors in it today that are going to be needed 5 years from now. So you're going to pay for those processors today. You're going to pay for that memory today, and anything else in that box that needs to be in there, you'd pay for it. And the non-mission critical was somewhere less than that, 30%. You know, rules of thumb. It varies from customer to customer, but I could almost count on certain ranges for certain customers, with mission critical being 60 to 70%. Interestingly enough, Ericsson did an economic study of the hyperscale data center, I believe it was a year or two ago, and in their study, they came up with 60 to 70%, which was exactly what I was using as a rough guide 10 years ago. So I felt somewhat of a relief to see that the numbers were staying steady, because when things change, it's really hard to track what people are doing. But it appears, from what I've seen, that things are still staying in that example of building a DAS-type box, that people over-provision way more than they should. So you can do virtualized DAS, and keep in mind, almost everything I've said now has been storage-focused. I'm going to spill into the idea of compute shortly. So in the case of virtualized DAS and virtualized machines inside boxes, this works to some extent. You know, if you think about what a typical server vendor will provide, you'll see three flavors, none of which quite fit anyone, but you can't have 1,000 SKUs. So what you'll have is the entry, the mid-range, and the high-end. And most people who do virtualized machines will build something with a high-end box. And for the same compute cycles, you pay more for that piece of hardware because it's more complex. You've got a bunch of NUMA stuff going on. You've got the ability to tie boxes together into multi-node. And this all has to be tested, and it all has to be guaranteed to work. Especially considered that's the space where people tend to run mission critical. And as a result, for the same CPU cycles, it costs more. That's well and good, but it costs more. And then you wrap complex software around it, and you get something that costs even more. In some of these cases, I'll see solutions where 80% of the solution cost is software. This is a really, really big deal when you build solutions that has, say, 60% more compute than you actually need built into it, and you're paying licensing for software on those cores, but the cores are running at 20%. It's kind of wasteful. So how do we fix these things? It's really complex, because one, the thing that engineers in general don't take into account, but they need to, is human nature. People won't change unless, number one, there's enough pain involved in the solution that they're forced to change, because change is risk. Risk can get you fired. Risk can ruin your company. So you've got to take the human nature into account. That's the first thing. The second thing is change never happens as fast as people think it's going to happen, because nobody rolls out things by the day. No one decides today. No one comes here and hears something that I say, and tomorrow they're running it. Everyone has cycles. Maybe your next cycle to roll out new hardware is a year from now, maybe 2. So it takes time. So it's kind of funny. You'll hear someone say, maybe it's just a headline grabbing stunt. They'll say something like, hard drives are going to be done in 2 years. Tape is going to be done in 2 years. No, it's not. It's not. It's not. In 2000, I remember, in the year 2000, I remember having a conversation with my colleagues about the imminent death of fiber channel. And we're 2018 and it's doing pretty well. These things don't die. There's always someone who holds on. So just take that into account. Take nothing away from what I say here, that next year everything is going to be composable infrastructure or rack scale infrastructure. It just doesn't move at that rapid of a speed. So what do we do? So first off, I'm defining a term here, software-defined storage. 1.0 was really the attempt for people to emulate what hyperscalers were doing. Hyperscalers went out, bought a bunch of hardware, made it all look exactly the same, wrote custom software to run on that, and made it work. And a lot of people said, wow, they're really, really efficient. That guy has a 2 square mile data center. That's bigger than my county. What's going on here? I can do that too, and I can make money and be efficient. But in the world outside of a handful of hyperscalers, you don't have everything in your data center that is exactly the same. Maybe you have HP servers, maybe you have some IBM servers, maybe you've got some Supermicro stuff, maybe you've got some Western Digital drives, some Seagate drives. It's different. And as a result, that one-size-fits-all piece of hardware wraparound just doesn't work. So let's try again. We'll say SDS 1.1, converged infrastructure. And that's the idea of, well, your stuff is a little different from this stuff, but we'll specifically test that config just the way it's done in the world of hyperscalers, and we'll make that work. And it does work, but it requires lots and lots of testing and lots of compatibility testing and things of that nature, and finding of bugs. One of the things I find it interesting how personally, I don't understand how anything works. After having gone through development cycles and seen the problems that get found, I lose all confidence in everything we're doing. After living, when I was in development, everywhere I've ever been and every company I've ever been involved with or worked and partnered with, you go through these development cycles where 100 bugs, 200 bugs, 500 bugs are found. And at the end, when there's no bugs, you're like, well, where's the next bug? You're just expecting it to come out of the woodwork. But this is what happens. You take a piece of hardware that's completely qualified, 100% qualified, and you put it in your hardware, which is 100% qualified, and bam, there was 80 bugs. It's horrific, but that's, you know, developers are the unsung heroes. I've lived it, and the pain, getting something right to be able to ship it it's incredibly difficult. So you see these problems, and what I'm referring to is SDS 1.1, trying to make these different configs and test them and make them all work. The overhead is huge. So we're back to where we started. Well, let's move to hyperconverged. And the idea of hyperconverged, once again, I'm not going to predict the end of hyperconverged. Hyperconverged is going to be around 20 years from now. It is what it is. It's actually a halfway decent solution. The idea of building units that has the compute and storage and memory that you need in the box and using that as a building block. I think it's going to exist and do well in the idea of composable infrastructure, but it does have some problems. One, if you can't change the building block, you're going to over-provision it to some extent. Disparity in the life cycles of the different components in this box. As an example, you stick some flash devices in this box, you stick some compute in this box, you stick some memory in the box. 3 years from now, maybe the processors are a little long in the tooth, but the rest of it especially in the case of flash, most flash devices are faster than the vast majority of people that use them actually need them to be. You know, they're using them as an accelerator or a replacement for hard drives, and they're 500x faster, and there's lots of leeway, but maybe something else gets long in the tooth. Well, there are companies out there that have like armies of young first-time engineers whose job is to take boxes apart and take out the pieces that are good and toss the rest aside. And it's a problem that's really difficult. And when you lock these things together physically, that's what you get, is people putting hands on servers. And oh, by the way, magically, when you take things apart, some percentage, 10 or 15% of the hardware never works again, strangely. You take it apart, put it on a bench, you put it back in, it doesn't work anymore. These things happen when you start tearing things apart in construction mode. So Usually hyperconverged is proprietary and expensive, and scaling is weak in the space. So even there, still problems. So what do we do? Well, let's start to identify the problems. And the things I've been saying, it probably sounds like I'm just knocking every single thing we've done in the industry up to this point, but I'm not. Every one of those are good solutions, and they've served their need, and they're not going anywhere. But they have weaknesses that allow room for improvement. And so that was my attempt at identifying the problems, and now let's actually fix them. What pain points this sent us down this SDS path? Well, I'll refer to this as SDS 2.0. And after I finish a couple more charts that are storage centric, I'm going to spill away from storage a little and start talking about the solution in and of itself. And I'm going to do that for a specific reason. Too often when you're in the silo of compute or in the silo of storage, you forget about the other half. And anytime you build something that's going to be composable or rack scale, anything in this fabric type world, you really need to be taking the other half of the equation into account. If you're not, you're building a SAN. You know, in the world of SAN, everything you do is concerned with what the storage does. And then you send things out on a fiber channel network and you have no idea what's going on the other side. And a solution like this needs to be a little more homogeneous. You have to actually be taking into account what the other side is doing. And that's what's happened here with things like Redfish, Swordfish, and even Western Digital's own Kingfish. These things are designed for allowing compute and storage to be managed with common tools. And this barrier between the two is being broken, and that's really what's needed to build true fabric type solutions. So we want pooled SDS that meshes well with pooled compute. That's the number one thing. We don't need a paradigm for storage and a paradigm for compute. The two need to mix. Think about the world of what goes on inside of hyperconverged. Everything is in the box. People manage those boxes with IPMI. People don't even know what IPMI is, and they're using IPMI. It's just ingrained in the solution as a part of it. So as this is replaced with something like Redfish, Swordfish, now you have Redfish for compute, Swordfish for storage, and as I mentioned, our own inside Western Digital is solution for managing is Kingfish, which is just an offset of Redfish, Swordfish. These things allow for homogeneous management and control, so you don't have to have these multiple silos and multiple ways to manage things, because it becomes very difficult to move forward. So you want standard protocols for accessing these things. You want really, really robust, reliable network. If you're going to put things on a fabric, you've got to have something that's designed for scale. And you really want a single network. You don't want some fiber channel network for storage, Ethernet, or whatever you're using for something else. And you want something that'll run both. Best of both worlds, the scalability of the SAN with DAS-like performance. And that's what we'll talk a little about. So problems we face. Data centers have these bottlenecks based to this unbalanced hardware that I talked to earlier. If you're building with a 50 or 60% over provisioning, which let's be clear, the hyperscalers are not, they're efficient. But everyone else is inefficient. I shouldn't say everyone else. A large portion of the rest are inefficient, and they're trying to move. No one's going to be as efficient as a hyperscaler without building to that scale. Scale adds efficiency in and of itself, but you want to approach that as best you can. So these DAS connections have been seen as the only way to pull this off, but there's opportunity here because we're doing things with our DMA that's adding, we'll say, 8 microseconds to the overall solution. So if I can put things on a fabric and mix the ratios that I need together as I see fit, and I can do that with, say, 8% hit overall with respect to the latency, that's kind of sort of a rounding error for a lot of it, for what you get for the efficiency. So those are the things we're going after. So let this be said, there's always an exception to every rule. There's a lot of people who won't need RDMA. In the world of, say, social media, the idea of social media, pick a company, you've got an account, you've got 1,000 friends. Those 1,000 friends are scattered over 100 countries. You post something, it's going to all of them. It's impossible for a social media company to control the locality of the data and have all your friends' data on one server because they're all tied to people, each one of them to another 900 friends. So it's impossible. So the structure of something like that is going to be built on the least common denominator, which is going to be internet. And so it doesn't matter if inside the rack I can get you down to 8 microseconds. Those solutions are going to be built in a different way.
You said internet, but you meant Ethernet, right?
No, I meant Ethernet. I meant wide area network. I'm talking people talk in North Carolina talking to someone in China. I mean, who knows what you're going through when you make a pass like that? You know, it's 100 milliseconds, 150 milliseconds. It's a long pole that. So inside the rack, maybe if you're at some social media company and this rack has 2 of my friends, but the other 898 of them are in another country, it doesn't really matter. So I've bought nothing but the idea of RDMA in a case like that. So that's the point I'm trying to make there, is just the locality of the data. There's no control over it, really. So there's different flavors for everyone. So that's what makes this so complicated. Nothing is going to be a one-size-fits-all, and none of these solutions are going to die, but there's a new one being born here with the idea of the fabric and composable infrastructure. So in the DAS configurations, we really want to disaggregate storage and compute. And as I pointed to earlier, here's why. You build a server. See, I'm starting to speed up a little bit. I'm looking at the clock. So growing pains inside the server, this is what I need. I need some network, I need some CPU, DRAM, some SSDs, maybe some HDDs. I'm an SSD guy, so I didn't put any HDDs on this drawing. But I do work for a company that makes HDDs, so let's just pretend a couple of those are HDDs. So there's HDDs in there, we've got this solution, this is what we've got to deal with. But I end up building this. I've seen it, I've helped customers when I was in the world of selling servers. I built this for customers. I helped them. We'd lay out solutions that were over the top. And I knew they were over the top, and so did the customer. But this is what they had to do, because they're like, I'm not opening this box for 5 years. I need this to be bulletproof, and I need it to have what I need by my projections for 5 years. So this is what we built. Well, this is kind of wasteful. I mean, but this is what we had to offer them, and this is what they wanted. So this is what they got. So let's not forget about the growing pains of the virtualized world and what happens with these migrations. We'll talk about this a little bit. So the idea is, if you build a virtual machine and you actually get around, so I would say, do you want to go with a virtualized solution? Maybe you get a yes, maybe you get a no. But if you go with it, the idea is you put enough VMs or VDIs, whatever you put in there, the idea is to go from 20% utilization in that box today, when you install it, to something closer to 100%. You're not going to get 100%, but let's say you get close. We'll say 95%. If one of those VMs, whether it's a cloud burst type growth, maybe it's just growth over a period of time, or maybe this VM just needs more than what you can give it for today, you can go into most web services and change the amount of resources that are tied to it pretty much by the hour, and just change these things. But if it grows too big to fit in this particular box, it's got to be migrated out. So if you think of the idea of cloud burst, and you think of the idea of rapidly growing and changing resources, like a living, breathing organism, if you're really close to 100% utilization, which is where you want to be for efficiency, the growth itself causes migrations, because it won't fit on the box because the box is full, so you got to pull it out. So there's a bandwidth give and take as the tide flows. And this is a problem in and of itself, because you're moving things back and forth. Maybe it shrinks and you want to put it back. You've essentially, it's like defragging a hard drive. Kind of sort of similar, but it's a data center. It's a defragmenting of the data center, moving things back to a more, so once again, once it shrinks, you're pulling it back, trying to be efficient again. So it's inefficient to some extent in a case like this. But in the world of composable infrastructure, you simply add another node. I having spent enough time in my life dealing with solutions that are started on a lab, where we're taking a soldering iron and tying pieces together, I think of it as a lab bench setup. You know, you've got a bunch of pieces, you tied them together, they're physically tied together like a DAS type config, and they operate like that, so you skip the need for expensive virtualized software, but they're logically tied together. You go in with, if it was Intel, it would be a pod manager. If, there's lots and lots of solutions out there, which I don't have enough time to talk about them all, but there's interesting discussions to have about several of these. You use this software, you tie some pieces together, and now you've got something that's been logically tied together. It's not virtualized, it's really hardware tied together, and it behaves more like it. So DAS doesn't really work, and for a number of reasons. It works for some people, but for others it doesn't, because this is expensive. What can we do? So the first thing that we have to do outside of the pieces is change the network. Now we know a big push coming from an SSD background, an HDD enclosure, if you're actually trying for performance of any kind whatsoever, you're probably not going to go above a 2 terabyte hard drive if you want performance. There's plenty of room to sell 8 and 10 terabyte hard drives. But if you're looking at performance and anything that you might consider an SSD for, you're going to do 2 terabytes or less. And the density is pretty low. And you move into SSDs, it goes up. But as we move into these new form factors designed specifically for flash, like the EDSFF stuff, the short and the long, I can get 8 of these where 2.5 inch drives go. And in the case of the ruler, it's really longer. You can put a lot more capacity on there. And the densities go up really high. The densities go up really high, causes all kinds of weird issues with a need to balance what's going on in the data center. So you need more network. So couple this with hard drives are much slower than SSDs. And if you look on the right side of the chart, HDDs and SSDs, the amount of overhead that's consumed in the solution overall with an SSD, a lot more of it is network. Hard drives are so slow, the network doesn't really play a portion. So once you get down in this space, and I'm looking for what I'm going to do with building the network, I really need something faster for those who want to do RDMA, want to do things of this nature. So you start building the solution, and you start looking at where the overhead is, and NVMeOF comes into play. So the idea, if everything moves to NVMe, and we build fabrics, and I want to be very clear, you're going to see fiber channel, you're going to see some InfiniBand stuff, maybe there's some OmniPath stuff being worked on that I'm not aware of, but there may be some OmniPath stuff coming out there. All these are fabrics, but really if I'm targeting the bulk of people in the center, it's going to be a mix of non-RDMA and RDMA and NVMe over fabric, because all the EDSFF stuff is going to be NVMe. That's the trend where the stuff is going. So protocol, I rip out SCSI, SAS stuff, I replace it with NVMe, and so I've made the device protocol better. I come at the network level, I rip out the SCSI layers, the TCP layers, replace it with RDMA and NVMe, and I make things a little more efficient there. Change these things, then you need bandwidth on the devices themselves. I was just talking about how bigger devices and more devices in a box, which come as a result of the EDSFF stuff, means all of a sudden I'm putting 12 by 8s or 12 by 4s, or maybe you'll have 36 EDSFF devices in a box. You need more and more bandwidth to actually take advantage of everything the device can do, which means lots of 100 gig links, or in some cases as we move on, you'll see 200 gig links and 400 gig links. These things will come into play. Everything affects something else. It's the butterfly effect here. The capacity of the devices affects the capacity density of the box. The capacity density of the box requires more bandwidth. More bandwidth means faster connections. If I'm using the box as a target and I'm burning CPU cycles in that box to do things with data, you move into RDMA to reduce that somewhat. So one thing affects the next, So the whole idea of the network and storage latency being improved, if you look at an SSD, as I showed on the other chart, the SSDs are so fast, a larger percentage of the overall transaction is getting consumed with network. So you see the left, well, we want what you see on the right, which is better and better network connections, which we're getting with the whole idea of RDMA coming into play and compute offloads. Compute offloads allow us to not burn cycles. There's a number of companies probably sitting in this very room that are producing network cards with 8 or 12 A72 ARM cores on it. And the idea is we move some compute down into the node. People who are building global RAID controllers running we'll say four enclosures getting ran by a global RAID controller in a RAID 6 type mode, what happens when there's a petabyte and a half in each of those enclosures and you've got to rebuild an enclosure in a RAID 6? You've been overwhelmed. So the idea of moving this stuff down into the box, this is where we start to see the effect of compute moving closer to the storage. The storage becomes so large that it becomes a gravitational force unto itself, where compute needs to move closer. And you'll see a breakup of host-based compute versus storage-centric compute start to happen as a result of these capacity points. The idea of putting a petabyte and a half in a 1U is real now, when it was ridiculous to even talk about something like that a year or two ago. But EDSFF and the smaller and smaller die that we're creating in the NAND world is making that possible. So, considering I'm getting really close to out of time, I'm going to speed this up a little bit. So, for any of this to happen, number one thing, and it's the thing I started on, one of the first things I said when we started, openness. It's surprising how well the industry has worked to provide open source type solutions. You're seeing things like Open19, OpenFlow, Open Compute Project. You know, the Linux Foundation's always been open, so is Hadoop. RISC-V, all these pieces are playing into one or another of these sensitive spots I just described in a way to provide something that will allow people to build such that you can have multiple sources. No one wants to build a 2 square mile data center and be tied to any one vendor who could go out of business or simply take the price up because it's proprietary. Everyone, at the scale we're seeing, everyone wants something that's going to be provided by more than one source. So it's really nice to see this come about. In the world of Fabric, the idea of what we want to see and what we're seeing happen is Fabric being built in a world where I provide compute elements, I provide storage elements. The compute elements are as simple as they can be so that they're as inexpensive as they can be. You tie them to simple compute bricks. You logically tie them together with some software package that you can get from a number of sources. They're not hard to find. You tie this together into a logically defined server. It behaves in a DAS-like fashion. If you need more performance, you move to RDMA. If you're doing something high performance compute, maybe everything's tied together with an InfiniBand, whatever the case, and you build these solutions. So I really want to touch on compute slightly, and I've got 5 minutes. So let's jump down to compute point. So I'd mentioned a new control point. As we get more and more capacity in the box, there's a need to pull compute closer to the storage. Maybe you have a case where you're building things on a Fabric. You've got 5 2-petabyte boxes. Huge amount of database, and you want to do a query. Do you really want to move 10 petabytes back to the compute on the other end on the Fabric? Huge amount of time to do that, huge amount of bandwidth needed. So you start doing things like do the query locally and send the results back. It's not that much different than, say, what Hadoop does. When you look at a Hadoop node, it's not much difference, but this will spill over into more and more examples as we move forward. You'll see a lot of what's going on with big and fast data starting to intertwine. People have come to realize, I talk to companies almost weekly who say, wow, this data I've been piling away, there's value. I can run analytics on this and get real valuable information out of it. So you're starting to see people say, I don't want to be on tape, or I don't want to be on low-end hard drives. I want something that's maybe not the fastest thing on the market, but fast enough to allow me to do analytics on this data. Maybe I can sell the data, maybe I can use it internally to do my own thing. Now, one of the things I've talked again and again about storage, but I want to touch on this. It's an especially big topic inside my own company, is the idea of compute. And I think we're right now at maybe 1 billion cores a year, with a target of the next few years of jumping up to 2 billion cores a year. And we're a storage company. We're not even a compute company. The idea is big data, fast data are starting to spill over onto one another because of analytics and things of this nature. And in the world of compute, RISC-V is an opportunity for open compute. and platforms that people can leverage without having to spill into licensed processors. And my own personal opinion, you're going to see all these processor types exist, and for a long, long time. But there's opportunities for spillover. One more example of an open hardware platform is the RISC-V processor. It's built to run big data fast, and memory-centric compute stuff, moving compute to the data, moving the processors closer to the data. I think you're going to see a bright future for RISC-V as well outside of storage. So, quick summary, and I think I'm out of time. I had 2 minutes. I'm right on. I had to skip a couple slides there, but I'm right on. I'm feeling good. So, summary. The fabric-friendly protocols, these methodologies, are really meeting individual pain points that are coming from specific customers. It won't meet everyone. Some people will still do SAN, some people still do NAS, but there's other customers who are trying to be efficient, getting away. If you've ever built, I'm sure there's someone in this room who's designed a solution that was 60% over-provisioned, and they want to get away from it without having to pay 80% of their solution cost being in some proprietary software. I've sold both. I've been involved in building both, and it's done, and now there's some opportunities for those who are doing it. Once again, if you can get by the human nature step of the risk and the pain and something different, there's opportunities to move off, and I think we're going to see a very bright future for the composable infrastructure, rack-scale architecture type of brick-based solution on a fabric design. These large capacity points can be created. If you grow to some capacity point and you need some more, you logically assign some more. You don't have to over-provision to start with, and you don't necessarily need a SAN to do it. And the bricks in general, as you move to common bricks with open designs, you provide lots and lots of capacity for multiple sources, and you get the lowest cost, you get the most simplistic design, and then you add software layers on top. A lot of it's free. Some people do their own proprietary. And players like the virtualized world, these guys can still play in the space too. All this stuff still runs. Nothing's been architecturally changed to prevent you from running the same stuff you ran in older architectures on the new. And one thing, and I should have made this either the first bullet or the last, the TCA considerations on the design. You've got to take the software savings into account. Too often, coming from a world of storage, too often people are concerned with the cost of the storage device without taking into account the value of the device. If I can give you a device and it costs 5% more than what I gave you last year, but that 5% saves you 40% on the top end because you removed some software package or something else, you've got to take that into account and understand the whole picture, or you're never going to get anywhere. I frequently said, as I've tried to make progress in companies I've worked for, and this has been going on for 10 years. It takes patience to get where we are now. But I would say if the people who designed a bus engine only concerned themselves with the idea of engines, they would say, my bus engine costs more than a car engine. This is a foolish thing to build. I won't build it. But if you take into account the value it brings, maybe this costs 50% more, but this hauls 5 people and this hauls 100. You take that account, it makes sense to build the bus engine. And these designs, if you take into account top to bottom and the full TCA, TCO of the solution, these are fantastic solutions that I think are going to have great treadway. And I am finished. Thank you.